The gas law stuff you've learned so far can be applied numerically in addition to conceptually by putting numbers to the pressure and volume that are going either up and down. As a quick fix, though, in the section called Combined Gas Law, make sure there's an equal sign in between your two sets of data because I forgot to put it there, sorry. Also, put a line through the N part of the equation. The N1 and the N2 stands for moles, and it does belong there. But none of my problems include it, so I don't want to confuse you with its presence. P1V1 over T1 equals P2V2 over T2 is your new equation. If you look at the far whiteboard over there, you'll see that I've got units of each of these things, and it shouldn't be news to you. You're familiar with everything on that whiteboard. However, on your cheat sheet, above where you see this equation, you'll see the listings of all the units that equal pressure, volume, temperature. Also on the cheat sheet, you'll notice that the relationships of pressure, volume, and temperature going up and down is listed above where the equation is. And there's some scientists connected to it that I didn't tell you before. For example, Boyle's law is what I just showed you. If pressure goes up, volume goes down, and vice versa. There's a scientist given credit for that law. Temperature and volume is Charles' law. Temperature and pressure is Gay-Lussac's law. I do want you to be aware of what scientists did what law, so add that to the flashcards that I know you're making anyway. What we're going to do is apply the same idea of one going up and one going down, or both going up, or whatever, to some actual gas situations. Pause the video to write down the problem. What this equation does is give you a before scenario and an after scenario of a sample of gas. This first problem uses a balloon, but the balloon's going to look like something, and then when you change the pressure or the volume or whatever it changes, it's going to look different. Maybe the balloon gets bigger, smaller, or changes temperature, or whatever. The 1s and 2s stand for before and after, the initial and the final. So we're going to analyze this problem to figure out what goes where. Now, we're going to run this problem the way we run most math in here and start by extracting the numbers with their units. So work along with me, starting with 2.75 liters. That'll be my first guy that I pull out of the problem, followed by 18 degrees Celsius, and then 45 degrees Celsius. So there's all my given values. Now there's going to be a question. What does this want us to find? Volume. It says find volume. List it the way I listed it here. Now, you should be familiar with these units, but again, if you're not, look at the whiteboard over there or on your cheat sheet. It's near the top in the Combined Gas Law section. What is liters units of? Volume, all right? And that is the first volume in my list. That's what the 1s and 2s stand for in the equation. What about degrees Celsius? What is that units of? Temperature. And that is the first temperature in the list. But then we have another degrees Celsius. So it's still temperature, but that's the second temperature in the list, and we want to know that final volume. Now what you'll notice is the equation has pressures in it, and our problem does not. That's going to happen often. What you do is you ignore the missing units. Since this problem doesn't use pressure, I'm going to pretend like the P's aren't there. And if you pretend like the P's aren't there, the equation becomes V1 over T1 equals V2 over T2. And then you just solve for that. V1 over T1. All right. My V1 is 2.75. over T1, but stop, look here. Most important thing I'll say all day. Degrees Celsius cannot be put into a gas law. Degrees Celsius can never be put into an equation. It's got to be that other temperature unit. What's the other temperature unit? Kelvin. You know how to make that change, though. How do I make 18 degrees Celsius become Kelvin? Add 273. 18 plus 273 is what? 291 Kelvin. There's another Celsius reading that also needs to be changed. 45 plus 273 is, you get 313? 318, sorry. 318 Kelvin. And now we're good to move on. Guys, if you use Celsius, you'll get different answers. And I'll usually make those wrong answers a choice. So be careful. Remember what we were doing. V1 over T1. The correct T1 is 291. Equals V2 over T2, so X for our V2, we don't know what he is yet, over T2 of 318. How do we solve this? Cross multiply. 291 times X is 291X, thank you. 2.75 times 318. You slipped the decimal there. 874.5. Divide by the number connected to the X on both sides. I get 3.01 liters. To recap, we pulled out our data, we connected the units to variables that are in our equation, and then we plugged in what we had into the equation. If we didn't have it, we ignored it. Let's do another one. We're dealing with a sample of oxygen here, so let's see how the oxygen changes when the problem changes its pressure, it looks like. Let's extract numbers. Now, this first step's the one that y'all skip most often on computer days, and you drive me crazy. It's the most important part. Pull out the numbers with the units. 59 mils. And then 0.68 atmospheres. 0.49 atmospheres, and again, this one does want volume. Identify what the units are connected to. Use the whiteboard over there to cheat if you have to. Milliliters is units of volume, the first one in our list. Atmospheres is units of pressure, the first pressure in our list. Atmospheres, again, is the second pressure in our list, and we want to know the new volume. Now, notice that temperature is not a part of this problem. Therefore, that Kelvin thing you have to watch for, because Celsius is always bad, won't be a problem here. There is no temperature this time. If we ignore the T's, the equation becomes P1V1 equals P2V2. So P1V1, P1 is 0.68, V1 is 59, equals P2V2. P2 is 0.49, and V2 is our unknown. Simplify. 0.68 times 59. 40.12. 0.49 times x. 0.49x. Divide by the number connected to the x. What do you get? Yeah, I get 81.88 milliliters. What does Boyle's law say? Somebody look at your cheat sheet. What does Boyle's law say? Find it. It's up there above the equation. If pressure goes up, volume goes down, and vice versa. They're inversely proportional. You can use that as a way to check your answer. Not to the point to where it nails it on the head, but to at least see if you went the right direction. Look at pressure here. What did pressure do? It went down. It went from 0.68 to 0.49. Boyle says if pressure goes down, volume must go up. And it did. Volume went from 59 to 82. So that supports that idea. So it's not a perfect way to check your answer, but you can compare it to the gas laws. Extracting info, 200 kPa, and then a couple of Celsiuses, 20 degrees Celsius, 31 degrees Celsius. The question is, find pressure. What is kPa units of? Pressure, our first 1 degree Celsius. Temperature, our first one. Then we get a second temperature as well. But we know that degrees Celsius is never okay. We need to add 273 to these. 273 plus 20 is 293 Kelvin. 31 plus 273 is 304 Kelvin. And now we've got temperatures we can use. If you ignore the V's, because we have no volumes, it would be P1 over T1 equals P2 over T2. So P1 over T1 is 200 over 293 equals P2 over T2. P2's our unknown over 304. Cross multiply 293 times x is 293x. The other way, 304 times 200 is 60,800. Divide by the number connected to the x. And I believe you get 207.51, is that right? I think you have one digit slip somewhere. KPA. And again, we said that temperature and pressure both go the same direction. Temperature went up, and pressure should have gone up. It did. So at least we have a reason to believe we did the right thing. Anybody get a different answer? Now, there's one last thing for me to show you, sorry. Because I know the burning question in your heart is, well, sir, are there any problems that will use all the variables? And of course there are. So we've got some crazy things happening to this sample of chlorine gas. But these aren't any more difficult, really. It's just more work. As long as your pre-algebra is all right, it shouldn't be any issue. Let's extract some numbers. 450 milliliters, 560 millimeters of mercury, 17 degrees Celsius, 0 degrees Celsius, 800 millimeters of mercury, and it says find volume. As usual, identify what's what. Milliliters. Use the top of your combined gas law cheat sheet. It'll tell you is a volume. The first one, millimeters of mercury, is a pressure. The first one, degrees Celsius, is temperature. The first one, degrees Celsius, is our second temperature at the 0. And then we're given a second pressure as well. What's the next step? Not plug it in. Not cross. Get rid of Celsius. Do not let that Celsius stand. 17 plus 273 is 290 Kelvin. 0 plus 273 is 273 Kelvin. Now we're ready to go. P1 V1 over T1. P1 is 560. V1 is 450 over T1 of 290. Equals P2 V2 over T2. P2 is 800. V2 is unknown. And T2 is 273. Unfortunately, we'll be dealing with some temporarily large numbers, but that's life. Simplify. I'm going to do just the numerators first. 560 times 450 is 252,000. Still over 290. The other side, 800 times x, is 800x. Still over 273. cross multiply for some largeness. 290 times 800 x is 232,000 x. $252,000 times 273, and you'll get my salary of $68 million. I would have retired by now. Divide by the number connected to the x. I get 296.53 milliliters.